I did put salt down, but I did this too. So we had like piles. So we had like piles of snow and ice in certain spots. What did I do to it? I actually did this. I'm not making a story up. I did this, and I didn't realize really what I was doing. I didn't understand the chemistry maybe at that point in my life. I was like a freshman probably. What was I doing? I spread it out. Yeah, I remember taking a broom and I was like spreading out because I had bumps and I was trying to make it smooth. I was going to try and play right on top of the snow and the ice. And I went inside, and then like 20 minutes later, it was all gone because the salt helped and the sun came out and it helped it evaporate even faster. So it actually worked. I didn't realize what I was doing. But I know this is funny. I teach chemistry now, so I think of things I've done in my life to kind of relate it to you guys. And that's something I just remember that day. So it was a great day. We went away, we played basketball. It was awesome. So anyways, yeah, if you spread out, the surface area, if you had a chunk of ice and you want it to melt faster, okay, smash it into little pieces. Same concept. Surface area does a lot. So increasing that surface area, it would evaporate very, very fast. Compared to just in here. If I let it sit in here, the water would take forever to evaporate. Throw it on the floor would work a little bit faster. Hopefully that makes sense. All right, so liquids evaporate only from the surface, and I'm going to explain a little bit more about that with the forces here. And if the surface area is increased, evaporation increases. All right, now here's a question. 2 questions for you. This is all about forces. 2 questions. I guess this was it. So question number 1 here. Why do liquids only evaporate from the surface, leave about maybe 3 lines? And then number 2, how does sweating cool us down? So why do liquids only evaporate from the surface, and how does sweating cool us down? So you're trying to answer this. If you don't want to screw up your notes, I understand. I really would like you to try and write it, but at least in your brain here, in your head, how come liquids at the bottom, right? Or how come particles at the bottom of this water bottle, how come they can't evaporate? So when I use you guys as an example, hopefully that kind of helps there. And then without sweating, we would overheat. I guess you could die if you got hot enough. Sweating, regulates our body temperature, cools us down, but how? And in lab, if anybody got the acetone on your hands when we were squirting it out of the syringe, what'd that feel like? Anyone in here get that on their hands? Cold. Yeah, it was like cold, right? It was cool. So if you spill something on your hand and it evaporates, it feels cold. Same explanation. Why? Why? Only a 10-year-old Mike Flower eats a Twix in the morning.
Jake Wyman eats brownies.
Yeah, I've talked to Jake about it. Didn't you tell me when you were a kid you had like a Monster and a...
Yeah,
what was it?
Oh, it was when I went to the Little League thing. Yeah, it was like 6 o'clock in the morning. I had Slim Jim and an amp.
Slim Jim and an amp. Breakfast of Champions.
Yeah.
All right, pair up and discuss your answers to these 2 questions.
Oh my God.
I'll give you about 2 minutes here. Yeah, if you know, share with Courtney.
Yeah, I'm not.
I know. I thought they were reinforcing when we're on the surface, we have one of the molecules like you're connected like below, but there's nothing on top. So but when you're like down in the water, then you're surrounded.
Yes. I got the opposite. I didn't get number 1, but I got number 2. I said,
I was thinking like if you're on the bottom, like particles
sweating
take
heat
up.
down
Yeah.
because you're transferring heat to sweat, which evaporates. Causes you to lose that heat.
Be free.
Okay, would you guys post first?
So, I can't put it in scientific terms.
Yeah. We're maintaining from this.
No, you're
Thank
fine.
you. Thank you, Miss, like when you're sweating, like you feel hot and like you can feel it. At least that's for me. I sweat. No, seriously. Yesterday I had to stop, so I was wearing a sweatshirt.
I don't even know his name.
Who? The guy with
The one with the jets back there. The little one strap just right there. Just chucked it. Maybe, yeah. I won 5 out of 6 games. Pretty upset.
That's about 2 minutes. Go ahead, move back. Here you go.
free shoe.
I like to play.
Before I forget, we're running out of time. This worksheet's due tomorrow, and I realize it's just kind of more like review on gases a little bit. There are some liquid and questions in here, but the one that I really want to give you, I didn't copy it. We're not gonna be ready today anyway, so I'll have to give that. I might give it to you tomorrow, do Monday. We'll see. So anyway, do just the circled ones here. Can't have 2 days in a row without homework. That's craziness. What's that?
We go a weekend.
Yeah, we're not done with the notes yet. After we talk about this, we're going to talk about table H, then we'll go back to the demo. And then we'll be good to go.
1, 2, 3, 4, 5, 6, 7.
I always do, and then I always overplay it in my head, always. I think when you're learning to be a teacher, they tell you, make sure you always have plenty to do because, I don't know, you ever been in a class where the teacher ran out of things to do or something? Don't answer that, but I don't want no games or anything. But when I was younger, you know, sometimes that would happen to me. So now I'm like,
Oh, yes.
bang, 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 bang. It's weird, right? It's weird. It's like, shouldn't we be doing something? So anyways, I was overplaying. Back to this. Number 1, why do liquids only evaporate from the surface? I heard your answer. It's very good.
Oh, mine. Well, I didn't think it was like this, but I said there was like weaker forces of attraction because they're not like totally surrounded by all water molecules like the bottom one.
Perfect. I literally couldn't answer it any better myself. Very good. Exactly. That's exactly why. Good job. If you guys look up here, here's the surface. There's nothing up here except air. Water's not attracted to air. It's attracted to itself. I know that sounds weird, but water, just like when I had you holding hands here, all these water particles are attracted to the ones below it. Okay? I mean, I could draw a whole bunch of lines connecting all these particles, but they're all connected to the ones below, and these are connected to the ones down here. So they're all kind of like anchors, right, hanging on to each other. But the ones in the middle, near the bottom, are like, Courtney says, surrounded. They're surrounded. This one right here is attracted in all directions. It's not going anywhere. It's on lockdown, okay? It's not going anywhere. But these have less forces. They don't have anything up here to be attracted to, so they have less forces holding them down. They're not surrounded. It's a very good explanation. So the particles at the surface have less forces of attraction. So it's easier to break them. Less forces of attraction. And the ones in the middle and at the bottom, so particles, we'll say in the liquid, not on the surface, in the liquid, are surrounded. So, oh, that's 2. So, they have more forces of attraction. And that's it. That's the reason. Okay? That's it. That's why the surface evaporates. Not just because it's on the surface. But because it happens to be on the surface, there's less forces. Now, what I was talking about with surface area should make a whole lot of sense. If this was the surface area, there's only 1, 2, 3, 4, 5, 6, let's say 6 particles at the surface. If I pour it on the ground and the liquid flattens out, are there more particles on the surface? Yeah, almost all of them would be on the surface. So that's why it evaporates faster, because there's more surface. So less forces for more particles. Right? This one here could be up to the top. It could be on the surface if I pour it out. So hopefully that makes sense. Number 2. Real quick, I bet you know, but real quick. Why do we sweat? Or when do we sweat? When we get hot. Okay, so that obviously has something to do with it.
The evaporation of the sweat takes heat energy from us.
Perfect. You two want to teach a class from now on? Maybe tomorrow? Good job. And if anyone else answered that, I don't know. I can't read your mind. Very good. Good job. All right. I can only give them credit because I called on them. But if anyone said that for this sweating, very good. Because that's not always common knowledge, right? How does sweating cool us down? The sweat evaporates off our skin. Evaporates off our skin, taking heat with it. Taking heat energy, we'll put / kinetic energy, KE, with it, thus leaving your skin cooler. It's the same thing with boiling water. The steam is hotter than the water itself. It takes energy with it. That's why water, when it boils, it gives off steam. It's trying to cool itself down. So boiling water can never actually go above its boiling point. So water boils at 100, it'll never go above 100 ever, because the extra heat goes with the steam. That's why it stays constant. It stays at 100, never goes above it. Same thing here. Your body should stay at a certain temp. It doesn't keep getting hotter and hotter as long as you're sweating. All right? You ever been doing something inside in the winter, sweating like a maniac, and then go outside?
Yeah.
What do you see? You ever see steam coming off people's heads or arms or whatever? Maybe not, but yeah, yes, that's exactly what I'm trying to give you a visual. It's literally taking the heat off of you and going into the atmosphere. So sweat evaporates off our skin and takes the energy with it. So why do we have to be hot to sweat? Well, this only happens if you give the sweat energy. So if you have some sweat on your arm but it doesn't have enough energy, it won't evaporate. That energy allows these forces to break free. Okay, water will evaporate on its own. So will sweat. But if you give it heat, it evaporates faster because you're giving it energy to break those forces even faster. So all this stuff's starting to hopefully make sense to you. All right. So now let's go to table H. And what does table H have to do with anything? Why are we looking at table H right now, Aaliyah? Why today, in class, at this moment, are we looking at table H? Very good. What's the title of the chart? Vapor pressure of 4 liquids. Good. Is everybody on table H? There's always somebody out there who's like scared to ask me or whatever. Doesn't want to tell me they don't have it. So make sure you're on this. Okay. Yeah, vapor pressure of 4 liquids. All right, I'm just going to ask you a random question. See if you guys can read the chart without me even teaching it. Who has the highest vapor pressure at 50 degrees Celsius? Which liquid? There's 4 liquids. Which liquid has the highest vapor pressure at 50 degrees Celsius? And remember, what does that mean? Because I'm going to follow that up with another question. So in our notes, we're going to write table H. Again, we're still under forces of attraction for liquids. Forces of attraction give liquids all types of cool properties. Table H. So let's write the question down. At 50 degrees, blank has the highest vapor pressure. Highest vapor pressure. And I'm going to start abbreviating vapor pressure VP, like probably tomorrow. And then at 50 degrees, let's make sure we really understand this. At 50 degrees, blank has the lowest vapor pressure. And usually when I'm talking about the reference tables, I'll project it up there and kind of do it with you, but because I'm recording, it kind of screw up the notes, so I'll just kind of hold it up. Anybody think they know the answers to these? How about Morgan Heath? Welcome back. Very good. Propanone. Can you tell me what that vapor pressure is? So what is propanone's vapor pressure at 50 degrees? It's an estimate because it's not right perfectly on one of the lines there, but. And everyone's doing this, by the way. What is vapor? We're just gonna kind of write it up here. What is the vapor pressure of propanone at 50 degrees? Morgan's got it. Well, okay. Well, I'll help you out. If you look at the y-axis, go to see where it says 50, and then you see 100, right? Right below that dotted line. What does each box represent on the y-axis? How much? It's either 10 or 5. 10. Good. Okay. So now let's go to 50 degrees. Go up to propanone, and then look left again. It's pretty close to what you just said. 80. So you were reading it right. So I would say, what do you guys think? 82? 81, 82?
A little bit before.
Up 83.
Let's agree on 82. We'll just say 82. So 82. So if you're confused how to read this, again, this is where I usually project it. Okay, look up here. You go to 50 degrees. You go up to propanone. Where's propanone? Propanone here, and then look left. So I'm going to say it's about, okay, that's about 83. And is it in kPa? Yeah, kPa. All right, good. Who has the lowest vapor pressure? Nicole? Ethanoic acid. Good. Ethanoic acid. I'll give someone a bonus point in their next quiz if you know what ethanoic acid is called in real life. Like in real, like normal people, not chemists. Layman's terms, if you will. Common man, woman. No bonus points today? Vinegar. Ethanoic acid is called vinegar in real life. Okay? Anyways, Nicole, what is that vapor pressure? Like 8? 8, yeah. So this would be 8 kPa. What does this mean? Ariel's going to tell us. At the same temperature, so let's say I had a beaker. I was wondering when that was going to happen. It seems to happen whenever it rains or snows. Ariel, let's say, the good news, that's on its own deal, so it didn't screw up. We have a beaker of propanone, a beaker of ethanoic acid. They're both at 50 degrees. One of them's doing this much faster than the other one.
The ethanoic acid is evaporating. Quicker, has lower flux.
You don't seem confident.
I think I am.
You think you are. What does vapor pressure mean? So if this was sealed, there's water in the cap. So if this is sealed, what builds up in here? Vapor, and when it collides with itself, it creates pressure.
Yeah.
So if there's a lot of vapor up here, will you have a high vapor pressure?
Yes.
Okay. And if there's not a lot of vapor, then you have a low vapor pressure. So if there's not a lot of vapor, is it evaporating?
No.
If there's a lot of vapor, is it evaporating?
Yes.
Okay. Still confident with your answer?
I don't know.
Did I thoroughly confuse you?
Yeah.
Good.
Good.
now you're confused and you'll figure it out. Okay, now you're like, oh wait, I don't know what to make of this, so now I'll fix it. So if a liquid produces a lot of vapor, does that have weak or strong forces?
Weak.
Weak. Does that make sense?
Yes.
Okay. So which one has a lot of vapor?
Propanone.
This one, and how do you know? So stay with me, Ariel, and anyone else who's confused, trust me, you're not alone.
Because it's got high...
High vapor pressure, which means a lot of vapor colliding. So if we have two beakers here, one sealed here, one sealed here, propanone would have a ton of particles up here bouncing around. That would be propanone. Ethanoic acid here, ethanoic acid would have maybe a couple. So this has a higher vapor pressure because the water or the liquid here doesn't hold itself together very well. It constantly evaporates. Weak, weak, weak forces. Here, pretty strong forces being held down. They're not evaporating. If there's not a lot of vapor, there's no vapor pressure. If there is a lot of vapor, there's high vapor pressure. Does that make more sense?
Yes.
I hope so. Good. So this is what we're writing. Propanone has very weak forces of attraction. Very weak forces of attraction, which results in a lot of evaporation and vapor, creating high vapor pressure. I'm just going to put high VP. So propanone on table H actually at all temperatures, if you look at it, at all temperatures has higher vapor pressure. So it is the weakest liquid on there. Ethanoic acid has the strongest forces because it has the lowest vapor pressure at every single temperature. And the other two, water and ethanol, are in between those two. So the concepts today that I really focused on is understanding why these things evaporate, how they evaporate, and then how it affects the pressure. And really it comes down to forces of attraction. So weak liquids have high vapor pressure, lots of particles, all right? And then this one has not a lot of particles, low vapor pressure. So actually what I would like you to do, if you can in your notes here, next to this one, I want you to sketch what I had there. So this one has a lot of particles up here. And then this one, ethanoic acid, only has a couple. Just so you have something to visualize, even if you understand it, copy just a little sketch down that the propanone, all types of particles coming off because it's weak. Bottom one, not so much. And we should have time to